Yeah. So yeah, we did talked about the AND gate. So now we'll go with the OR gate. Okay. So same as AND gate, right? So that the name itself we will just decide something, right? So from the name itself, what we can imply that if you see, right, it's OR. Before that it is AND. So what we told, since it's AND, so both of its inputs need to be high, then only the output will be high. So this is what we just completed our AND gate. So now with the OR gate, if you see, right, if you see OR, so any one of the input could be 1 to make the output as high. So it's at least any one of the input should suffice to be 1 to make the output as high. So that is what the OR will imply. So it's a OR, right? So A or B, like any one of the inputs could be high to make the output as high, not like AND. So here also we'll just try to write the truth table. As I told, like for AND gate, so what we will have, like input combination, we could write 2 inputs we have, so we will be having 4 combination of input combinations we will be having. So OR gate, as I told you, right, OR. So what we are going to do now, OR means any one of the input high is enough to make the output as high. So here you are seeing B as high, so your output will be high. And here also you will be seeing one input as high, any one of the inputs, right, minimum actually. So as a high. Here also you are seeing 2 inputs as high, so it will be high. Minimum it should suffice, right? Any one of the input is high. So like 2 inputs also high, also no issues. Yeah, we can just make it as high. Yeah, otherwise it will be 0. So this is the truth table of the OR gate. So this is understand, right? Yeah, it's the same as like this, but the like from the gate name itself, right, AND gate or OR gate, that itself we could come to know that AND gate is it has a requirement that its output will be 1 only if both the inputs of that will be is a 1. Same as for OR, the functionality is OR. So any one of the input is high is enough to make the output as high. So that is what we understood now. And the symbol of that, so if you see here, it is just this one is the symbol of OR gate, A, B and out. Okay, so this is a symbol of OR gate. So same like that we could write the expression also. Okay, so here out will be, there is some OR operator, this one, so out equal to A or B. So this is that expression of OR gate. Yes, so this is all about the OR gate. Yeah, we'll just go to the next gate, that is NOT. From the name we could understand that NOT is not like it's like just an inverter, right? So it's a NOT, so it will just like a inverter. So here also it's like inverter, right? So it's just inverting the input. So for that we no need 2 inputs and all. We here as a NOT gate, it will just do like out A and only one input it will be having. So here for one input, how many combination we could write? Since it's a binary, as we told before, here only 2 combination we could write. So out will be the inverted version of the input. So you will be having 1 and 0. This is just an inverter. So this is what the truth table of the NOT gate. Okay. So yeah, same for the symbol, will just to go ahead with as the same format as that. It will be like this, the inverter. It will be A, this is B, A bar or out. So here it's out, so output equal to A bar. A bar is just a simple to indicate that it's a inverter. Okay, so this is a symbol. And expression, yeah, that expression only I has written already. So our out equal to A bar. So this is what the expression of the NOT gate. Okay, so as we see, only these are all the basic logic gates. So and or and not. So among that, and we know the functionality is if both are high, it will be high. OR means both, any one of the input should be high to make the output high. And NOT gate will be the inverted version of the input. So that is what about the basic gates. So generally in our basic building block, right, basic building block of any of our RTL design, it will be the logic gates. So before that, it will be the some physical design related things will be there, but yeah, as a logic side, if you look into that in that perspective, from the logic side, the first thing we should be knowing about the logic gates. So these are all the basic elements of any of our design, RTL design. Okay, so this is what about the basic gates. Okay, so these are all the basic gates. Okay, as to about universal gates, we'll talk in a different video. In the next video, we'll talk about the universal gates and why we are calling as a universal gate, and as well as how we will be implementing this basic gates using our universal gates. So that and all we'll discuss later in the next video. And all we'll be talking about here. Okay, just we'll talk about all the gates. Okay, so and after that we will be having some gates that is like NAND and NOR. Okay, that we are calling as universal gates, but that will take it in separate session, that need some more extra discussion to be happened before that. So we'll just talk about the truth table expression and symbol in this video, and hereafter in next videos and all we'll talk about deeply about those things. Okay, so NAND gate is nothing but, from the name itself, right, you could like, this is like N plus AND. Okay, so this is the NOT plus AND. N means nothing but the NOT gate. So we will be having one NOT gate and AND gate functionality together in our NAND gate. So that is what the NAND gate means. So I will just give you the symbol representation of that, then you will understand something. Okay, since the A will be this, B will be this won't be you all know, right, this AND gate output will be AB. So the inverter means it will just invert the input. So the AB, the whole bar, will be the output of NAND gate. This inverter. So this is the NAND gate. Okay. So AND gate followed by the NOT gate will operate as NAND gate. So this is what the functionality of NAND gate. So as for the functionality, what we are going to discuss is nothing bigger than the AND gate. It's the same as AND gate, just an inverted version. So AND plus NOT is a NAND gate. Okay. So okay, we can just write the truth table, right? As we now only we have written the AND gate, we can just do like we already what we have discussed in the AND gate. If that is AND gate, both input should be 1 to make the output as 1. But here it's a different scenario, exactly the opposite of that. So if both inputs are 1 only, our output will be 0 and others will be 1. Since we have a inverter at the output of our AND gate, we are seeing this particular difference. Okay, just an inverted version of AND gate. So symbol, as we know, symbol how it will be. Okay, so just an AND gate you draw, and to mention this as an inverted version, you just add a bubble here at the output of the AND gate. This is just the symbol of NAND gate. Okay, yes. And yeah, expression wise we know, yeah, AB and whole bar, it will be the inverted version of that. So this is the out equal to AB the whole bar. This is what about the NAND gate. This is not we don't have any much difference from the AND gate, only the inverted version. So all others are same as that. Okay. Okay. Yes, this is what about NAND gate. We'll just move to NOR gate. Okay. So NOR gate is nothing but same as this is we could come to know, right? Same as NAND gate, this will be OR plus NOT or NOT plus, and we can just implement, but yeah, we can just tell that, but it will be like OR plus NOT followed by the NOT. So this is what the functionality of that. So just to draw how we could, same as NAND, it will be OR followed by an inverter. So we all know this will be A or B or A plus B, something like that. We can just call it as A plus B also, because this is something like addition, that is something like that one, right, multiplication. So we can call it as A plus B also. So A plus B the whole bar is the NOR gate operation. So this is what the NOR gate. So simply we could write the truth table same as that. Well, we'll fill it up the inputs first. Then as we know, any one of the input is 1, any one of the inputs is 1, we can make it will be 1 in OR gate. So we'll just reverse that, that means just invert that. So if any one of the input is 1, we'll just make our output as 0 0 0, else we'll make it as 1. That's all. So same symbol, if we go to the symbol side, it will be the OR gate followed by the bubble to make it as OR gate. Okay, a plus b the whole bar. This is the NOR gate. This is the NOR gate expression. Okay, yeah, this is also same as the OR gate, just an inverted version. This is understand. Yeah, okay, these are all telling this is universal gates. Then we'll go for some extra gates, like some special gates, that is XOR and XNOR. Okay, XOR and XNOR. So we'll just talk about XOR and XNOR after that. Okay, so XOR, XOR, okay, exclusive OR. This is something like that. X means exclusive OR. So this is like yes, how we can tell this as exclusive OR. Some OR operation will be doing. Before that, we will be having like some exclusive thing. Like how we can tell exclusive. Both the inputs should be exclusive to make the output as high. Okay, both the inputs should be exclusive. It should be exclusive to make the output as high. That is what about the exclusive OR. Okay, if I make a truth table of that, okay, the symbol of that I'll tell you this. Okay, it will be A exclusive or B. Some other things also there. That also will make it as this one only. What is that? Exclusive or up symbol, but generally we'll use this one. Same like that we'll fill it up. Okay. If I am telling that, right, it should be exclusive. Exclusive means if you see both are different here. In these two places only both are different. So here only both are exclusive. In other places these are similar. So if both are exclusive only, we will be making our output as high, or it will be 0. So this is about the XOR gate. Both of the inputs should be exclusive to make a output high. Okay, so this is what about XOR. Okay, parallelly we'll write about XNOR, because this is same like, right, XOR followed by one NOT gate is called as XNOR. Okay, same as NAND or NOT gate from the AND or NOT respectively, right? So same as that, here also it is something like that. So straight away we'll write this one. So here also it's a bar, so inputs will fill it up. Okay, here you can itself tell that the inverted version. So if both are exclusive, we'll make the output as 0, then else it will be high. So this is what about XNOR. Okay, I think it's clear here. So yeah, so this is what about XOR and XNOR. We'll just go with the same. The symbol, right? Symbol will talk about, it will be some XOR, right? So it will be like this. So A exclusive or B. Here also same. I think you could guess that it will be the bubble here to tell that it is inverted version. Okay, these are the symbol. Same we have, right, the expression. Yeah, here only we could talk about the expression. Okay, so okay, how we could write the expression for this? We could write yeah, that one, the whole thing about how we will be writing the expression from the truth table. I'll just tell you here about the XOR and XNOR. Yeah, from that you could just follow up that one for the other process also. Yeah, but we'll start from here. This is the output, right? So for this only we are going to write a expression. This is the output. So for this we are going to write an expression. So here, while writing the expression to the truth table, what we are going to you have to do, you should be seeing the first the high values, that means 1, where and all we are having the 1, because here we are going to write in the format of like sum of product. You may have in your digital electronics and all, right, sum of products is like it's a sum of products, right? Sum of products. So products will be the first step, then we'll just sum it up. So since we are summing up in that products, we should be concentrating on the high. Okay, so any one of the thing is high means it will be making the output as high rate. Any one of the product is making the output as high, the sum of the products will be high. So what we should be, the same like OR gate, right? So we should be seeing one thing, actually this or this. If anything is coming, it should be high. That's why I'm putting OR operator here. Like I will be seeing this one, this output set of input, this output's corresponding set of inputs, and this output corresponding set of inputs. If any one of the thing combination occurs, my output will be high. That's why I put a OR gate to doing the OR operation. I'm putting a plus here, and the products I should be seeing for this one. The product should be making us high when this combination occurs. So for that, what you could do, directly 0 and dot 1. If you add, definitely it will be 0. So to make it as high, only during this combination, it should be A bar. If your A input should be 0, then only your A bar will be 1, and it will be ANDed with B to make your product as high. Okay, so A bar B. Since A should be 0 to make our product high, we are just having A bar instead of A. If I put A, it will be 1 only when A and B are 1. So I no need for this scenario. I need for this scenario only to be my output to be 1. That's why A bar B I put. Then this combination same, A B bar. So this is what we should be writing our expression from our truth table. Okay, so this is same as here. If you see, right? Yeah, I will just parallelly write this also. You'll understand. Yeah, here also 1 we have, here also 1 we have. So this one and this one same as sum of products only, SOP only we are doing. So here we put a plus first, then we should be adding our products. So first product will be A bar B bar, yeah, as you all know, and 1 means A B. So any one of the product will be getting output as high, our output will be 0. So this is what we should be writing our expression. Okay, yeah, so this is all about all the logic gates. In the next videos and all, we'll be seeing about the universal gates and XNOR gate applications, and yeah, we'll close the logic gates in the next 2 videos at least. Then we'll go for the other combination and sequential circuits. Thank you all.